Thank you very much. Thank you, the organizers, for the invitation to give this 1-hour lecture. And I was here in 1982-83, the first year of operation of MSRI. I started working on inverse problems actually that year. I worked before in macrolocal analysis. And MSRI has been extremely useful for me, and I hope for the young people here. It's also started completely new field at that time. And organized programs 2001 and 2010 on inverse problems, and have a long-term association with MSRI. So what I want to talk about is applications, some applications of macrolocal analysis to inverse problems. The philosophy here is follow the singularities. So you want to know where singularities go. You send waves, those are singularities in some sense. And then you follow them and see what happens, how it interacts with what you want to find. And then use that propagation to recover the properties of the medium. So inverse boundary problems in general is whether you can recover the internal properties of a medium by making measurements outside the medium. It's non-invasive method. You don't want to penetrate here. And the prime example, the one that has the most applications perhaps, is X-ray tomography that led to the development of CAT scan or CT scans. You have a source of X-rays and a detector of X-rays, and you move the source around, the detector around, and by measuring the attenuation of the X-rays, X-rays travel approximately in straight lines. They are high-frequency electromagnetic waves. Can you recover the density of these different tissues? Can you recover the properties of the tissues? You want to image what is inside, for instance, if there is a tumor or there is a problem there. So Radon actually considered this problem not for the physical motivation, just for completely theoretical reasons in 1917. So let me tell you his discovery. He was interested in recovering a function from the integral along lines. This followed the work of Funk of integration a function along circles on the sphere. So here is the situation in 2 dimensions. You have a source and a receiver of X-rays. They propagate approximately in a straight line. You take the normal to the line, call it theta here, and modulo of S is the distance of the line to the origin. And there is f of x is the unknown function, the density that you want to recover. This is a section of the 3-dimensional body. And Beer's law says that the derivative of the intensity is proportional to the attenuation. So it's minus the derivative of E with respect to x is minus f, a multiple of minus f. So the intensity of the detector by solving the differential equation is e to the minus the integral along the line of the function of the density of the source. So you know the intensity of the detector, you know already the intensity of the source. You can recover this, and taking the log, you can recover the integral of the function along the line. And that's what's called a Radon transform. Already Alan defined it in quite a lot of generality. The Radon transform here is integration along this line, parameterized in this case by the normal and the distance to the origin of the function against Lebesgue measure on the line, the standard measure. And so you recover this integral of the function along lines. And Radon found a beautiful formula how to recover the function from the Radon transform. So you differentiate the Radon transform, you perform this operation which is singular, so you have to take principal value here, x theta minus s, and then you average over all directions. So you take all the directions of the lines, and up to a constant, you recover the function f. Beautiful formula, and the discretization of this formula is called the filter back projection algorithm, and that's what's used in most CT scans. The development of CT scans by Cormack and Hounsfield received the Nobel Prize of Medicine in 1979, I believe, 40 years ago. So this is an inverse problem, and we can say a lot about this inverse problem. We can solve it explicitly. Most inverse problems you cannot solve it so explicitly, but this is an example we would like to achieve. So there are two types, generally two types of inverse problems. One I will call linear, where the propagation is independent of the medium. So high-frequency rays don't see the medium. They attenuate, but don't see the medium. So there's no scattering. And this is X-ray tomography, and this you can have here a very good image of the brain. There is other methods called positron emission tomography, magnetic resonance imaging that uses a magnetic field instead of X-rays. This also uses X-rays plus a radioactive substance that is injected. So there are these methods that use the radon transform as the mathematical background. But nonlinear methods that you have is scattering. So for instance, you have a medium with index of refraction or sound speed. You have a source of sound and a receiver of sound. The propagation is not anymore along straight lines. These curves, which are of a lot of interest, are normals to the wave fronts, and there will be geodesics of sound metric, as we're going to indicate later. And this is used in ultrasound. This is transmission ultrasound. You try to recover from this information the travel time. How much time does it take to go from source to detector? You try to find what the index of refraction is. Of course, when you have reflections, singularities in the medium, you get the reflections back, and then this is also used now routinely in pregnant women. You can make an image of the inside by measuring the travel times of the echoes. You send waves, sound waves, you measure the echo, and from that you create an image. So last week, Katya Krupchik gave a lot of details about this another inverse problem, which is also, there's a lot of scattering here, which is called electrical impedance tomography, or Calderon's problem. You have electrodes around a body. You inject voltages, and you measure the induced current flux. And from that information, you try to recover the conductivity inside. So it's a different parameter than here. Conductivity measures how much electricity is being conducted from one point to the other. It's very different from this because currents go all over the place immediately. There is infinite speed of propagation. It's a very difficult inverse problem because the information is diffuse at the boundary. So you try to recover from what you get at the boundary, what was the conductivity inside. That's a very interesting one. So I'm going to talk mostly, my intention is to really talk more about this than this. I don't have time to talk about that problem, but you can take a look at Katya's talk last week. I think it will be available or is available online. There are other methods that have recently been developed called hybrid methods, which is a combination of two waves to get the information. Because ultrasound, for instance, that's very high resolution. You can get very detailed resolution in the image, but it doesn't give you good contrast. For instance, doesn't see very well a tumor. But however, optical waves, electromagnetic waves, are very good to detect contrast. So you try to find a way to combine both to get a better image. And there's something called photoacoustic tomography or thermoacoustic tomography, depending on the frequency of the wave that you send. And this is based on the photoacoustic effect, the sound of light, which was discovered by Graham Bell, who invented the telephone. This was before he actually found the telephone. he tried a wireless telephone by observing the following. When rapid pulses of light are incident on a sample of matter, they can be absorbed, and the resulting energy, the medium is heated and produces sound waves, and you measure the sound waves outside. So it's the sound of light, because from an electromagnetic wave, so you create sound, and you measure the sound outside, and from that you try to get the properties of the medium, like conductivity or the other optical properties. And this is a cartoon. You can find it in Wikipedia. You send a rapidly varying laser here. It hits, is absorbed. It hits the tissue, produces thermal expansion that produces an acoustic wave. That's an ultrasound acoustic wave, which is measured outside. And from that information, you try to find the properties inside. You try to create an image of the inside. This is a very promising method that you probably, the young people here, are going to be seeing hospitals in one day. And you can create very detailed images, for instance, of the vessels around near the skin. This is a very detailed method that you cannot get with ultrasound, because blood is very highly conducting, so it's very good to contrast. So you're combining this ultrasound with electromagnetic waves, and you can also see here the carcinoma very clearly. Li Hong Wang, who was at Washington University and now is at Caltech, has been one of the people doing the experiments on this method. So mathematically, and this is a motivation, partly motivation for what I want to do, you consider the wave equation with the sound speed here, and I have solved Peter Hind's problem, and this is the sign that I chose. And here is the initial data is the absorption. Here h of x is the thermal absorption, how much has been absorbed at the tissue. Then you try to recover this by measuring the solution U outside. And once you know the thermal absorption at every point, you try to create, from the second step, you try to find the optical or electrical properties of the medium. So you solve the wave, an inverse problem for the wave equation, and then you get inside information. You find the source here. With the inside information, you try to create to find the optical properties. Okay, so I'm going to get to that type of problem. I'm not going to solve that problem in particular, by starting with a much simpler case. So I take a compactly supported smooth potential. The support is contained in a ball. So here is the situation. Sorry, that's my phone. So here you have a potential, compactly supported, Q of x. And I'm going to send a plane wave, which is a delta function in the past. So omega is the direction, the normal to the plane wave. So this is t equal to x dot omega. And I'm patient, I wait a long time, and I want to see what happens afterwards. And from the inverse problem will be if we measure the wave for large enough time, can we recover Q? Or you measure it for large x. So this is a typical scattering problem. So you send waves, and you can vary the direction of the waves in different directions, and you measure what happens after it interacts with the potential, and from that information you try to find the potential. And this is where microlocal analysis of propagation of singularities come into place, because we can solve this problem. At least find the singularities. So you have the wave equation. We're able to solve it in time and position. And this is a plane wave in the past, like here. And the definition of a plane wave is just the Radon transform. So you integrate this function along this plane. So how to solve that problem? You observe that this solves the wave equation. Box is the wave equation, as earlier. It's very easy. Any function of t minus x omega, that's why it's called a plane wave, solves the wave equation. And when you take this as the solution, the wave equation plus q of that is going to be q times that. So you don't have 0 like you wanted. So the next try, which is the basis of what's called the progressive wave expansion, is to try the delta plus something smoother. So this A1 will be a smooth function, and H is the Heaviside function. So it will be a function which is 1 So you have your plane wave. So it's 1 here and 0 behind. And that's also a solution of the wave equation. It's 1 degree smoother because the derivative of the Heaviside function is the delta function. So you try this. You observe that this is also a solution of the wave equation. We try this. This is 1 degree smoother than this. So in order to solve that, you do the calculation. You get q plus 2a1. We need to find the amplitude here of this wave. So you do the calculation, and then you try to eliminate the main singularity here. The main singularity is delta of t minus x omega. So you set this equal to 0. So you get that the gradient of A1 is equal to dot omega. That's easy to, this has to be 0, is equal to minus q over 2. And A1 is equal to 0 if x dot omega is sufficiently large negative, because you want it, you just want the delta function as your solution in the past. And you can solve the problem explicitly. A1 is equal to this, minus 1/2 times the integral of the potential along the line in the direction omega. So here you have your potential, Q. You want to find the solution at some point. You integrate along the line up to this point with direction omega. And if you look at, after it has interacted with the potential, you look outside, you get the X-ray transform of the potential, the integral of the potential along the line is Radon transform in 2 dimensions. So if x omega is sufficiently large, you are outside the support to the potential. You are here, then you get the integral, the whole integral of the potential. And this is what's called the X-ray transform of the potential, minus potential over 2. And in 2 dimensions, the X-ray transform is the same as the Radon transform. So this is the X-ray transform. You take a point and a direction, you integrate the function in the line going through the point x with direction omega. Okay, so we have solved the problem, but still we have a remainder term. Because we haven't solved it exactly, we just eliminated this term. We still have this term. We need to eliminate this term. So what do? We add a term which is even more smoother than the previous term, less singular, and 1 degree smoother. The derivative of this is equal to the Heaviside function. What is S plus? S plus is S for S positive and 0 for S negative. It's also a progressing wave. It is supported when t is bigger than x dot omega. And then to eliminate the singularity, you just solve this equation, the gradient of A2 dot omega, the derivative in the direction omega is equal to this. And so A2 will be just the integration of this function along the line and so on. So you can keep going. Of course, you're not going to solve the problem. You're going to have a remainder. And then you kill the remainder again, and with a progressive, smoother term. So this is the induction. This is the continuation problem that I'm trying to solve. Is you keep going and getting smoother and smoother waves, plus a term which is already Cn minus 2. When n is sufficiently large, this is quite smooth. And using the ideas that you have seen for pseudo-differential operator, how to sum symbols of degree of homogeneity lower and lower, you use a Borel-type lemma to get an asymptotic expansion. And you can, the references here are at the end. This is done in full detail in a book that will never appear, but the notes are online with Melrose. You have this. You can sum up all the way to infinity this series. You can make sense of this asymptotically, but you get, of course, a smooth error. And this is an example, prime example, the solution of the wave equation, the continuation problem. Is a conormal distribution to t equal to x dot omega. And how do you get the potential? The potential is going to be obtained by the integration of because the term A1, which is related to the symbol of the wave, after you have this plane wave, you take u minus that. The symbol is related to this function, and you will get the integral of the potential along the line. Okay. By the way, another representation of this in the way you have seen before is as an oscillatory integral is this. You just take the Fourier transform, and you take this. You have to cut it up near 0. The Fourier transform of s plus to the j is 1 over rho to the j away from 0. And so you get this very classical symbol here. This is homogeneous or lower and lower degree plus a smooth term. This is to cut it up near 0. It's a cutoff near 0. So the singularities, of course, are here when t is equal to x omega. The progressive wave expansion tells you that nothing happens to the singularities as expected. You have this, maybe I'll write it here. You have the plane wave coming in. In terms of singularities, you have this coming in. In terms of singularities, you have the singularity also in t equal to x omega. Something here and here, maybe. Well, actually, it's here. But the singularity is still at t equal to x omega. Nothing happened to the singularities. We know this for propagation singularities. Here, the singularities are going to propagate along straight lines. So you are going to get the same singularity before. This is a demonstration of that. However, the principal symbol of this conormal distribution, u minus the delta function, which is you can compute explicitly, is related to the A1. Is determined by A1. You can recover the integral of the potential along the line, the X-ray transform of the potential, and therefore the potential, because we have an inversion formula for the X-ray transform, which I will actually mention in detail. So that's it. So you send your wave, and you can recover the X-ray transform of the potential if you wait enough time. So this is a picture. You start here at t equal to minus r, away from the support of the potential. This is the support, and you measure it here, and then you get the integral of the potential along this line. And you vary the line, and you get all the integrals of the potential. So that's how the X-ray transform appears. And to study the X-ray transform, it's very easy to show that you really only need to define it for directions perpendicular. So you take, this is the definition of the X-ray transform. It's by making this, is the same as f of x minus x dot omega. This is perpendicular to omega. So it's really defined on the perpendicular direction to omega, which is like Rn minus 1. And then you take the direction omega. So these are the lines going through omega perpendicular. That's the X-ray transform. This is x is in the omega perpendicular. That's the same thing. And you take the formal transpose, which means the transpose of the X-ray transform. You just take a point. You want to calculate the transpose, and you integrate over all the lines going through the point. It's very easy to show. This is an exercise that this is the transpose of the X-ray transform. You can calculate it explicitly. It's here. Integration over the sphere of all the lines that go through the point omega, so the point x, sorry. And then it's an easy exercise, which I will actually solve for you roughly later, is you compute the normal operator that several people here have talked about. Is this very simple singular integral, has singularities on the diagonal, it's a pseudo-differential operator, and you can do this for compactly supported distributions. So we can invert it. So this is one of the main examples of pseudo-differential operators that are not differential operators, square root or powers of the square root of the Laplacian. This is very simple. It's minus the square root of the Laplacian, and then you can invert it exactly. So you have the normal operator times the square root of the Laplacian is equal to f. And this is equivalent to the Radon inversion formula in 2 dimensions that I gave at the very beginning. It's a much simpler way. This is not the way that Radon did it, but it's a much easier way to get this formula. But this is a non-local formula, and also Radon's formula was non-local, it's equivalent. Because of this operator is a convolution operator. It's a pseudo-differential operator. Singularity is only in the diagonal. So it's not local. You need to know, in order to find this, you need to find the function, to use the values of the function everywhere. And the non-locality of the operator is a problem in practice, because you're using this formula or equivalent, the equivalent formula of the Radon transform. It's non-local. So if you want to find what's happening at the point x, here is your lever, or where you're trying to find, to make an image. You take a small neighborhood. You need to find. You need to use these X-rays, but also these ones. Because the formula is non-local, so you need all the angles, all the rays. And this, of course, is not practical. You cannot do this in practice. You cannot take X-rays that are away from this. I mean, also X-rays are radiation. So you would like to find a local inversion formula, if possible, that gives you information. And this is where macrolocal analysis helps. Because if you multiply times the square root of the Laplacian, you have this formula. You multiply both sides by the square root. Then this is the Laplacian now. And this is a local operator. And this is, but of course, this is a local inversion formula. You're not recovering f, but the square root of the Laplacian of f. But however, from the point of view of singularities, and a lot of the times is what you want to do, the wavefront set of this is the same, because this is an elliptic pseudo-differential operator. So it preserves singularities. Therefore, you're not recovering f, but you're recovering the singularities of f. And if you want to recover how much it jumps, also you can do that. You can look at the symbol. And this has been given a name, local tomography, and I give a reference here for data, but it's a very simple application of macrolocal analysis that's used in practice. Of course, an example of where this is useful, you have here I drew 2 domains, but you can have several domains, say with smooth boundary, with a function jumps. It's a characteristic function. You have some value here, given by these coefficients, and jumps here. And you can recover where are the singularities of this function by the X-ray transform, and how much it jumps by looking at the symbol. So this is the applications of local tomography. Okay. But as I said, this is for the wave equation plus potential. This is simpler than the acoustic wave equation because the coefficient that you want to recover is in the lower order term. But suppose you want to do the same for the acoustic equation. So you have a plane wave here. Oh, I can't do it here. Okay, so you have a medium here, and the sound speed is supported here. So that supported means that C of x is 1 outside some set, or outside some ball. That's the index of refraction. C of x is the sound speed, or the inverse of the index of refraction. So this is the acoustic wave equation. And again, I have a plane wave coming in. And it will interact. So this is t equal to x omega. This is the delta function. It's concentrated on this plane, interacts with the sound speed. Something happens. And the inverse problem is, you know, u for tx omega for t sufficiently large, can we recover the sound speed? This is a problem that arises, as mentioned before, in ultrasound and in geophysics as well. And for the people interested in geometry, you can also take the wave equation associated to the Laplace-Beltrami operator, and you want to recover the metric. Okay, so in this case, we're not going to be able, and I give this as an exercise, you're not able to just take the plane wave. We know that singularities are going to propagate. So you are not going to have t minus x omega that before, but we'll have a phase function here. We'll have a distorted plane wave that we want to recover, times some amplitude. And again, the Heaviside function here, there's some smooth amplitude, and then you have a smoother and smoother contributions, and then a smooth function. We want to write the solution this way. This is the continuation, I call it the continuation problem. Okay, and then what is the main singularity? Now, we don't have a solution of the wave equation. This is not a solution of the wave equation. What do you get? You get this equation as the highest order singularity. The highest order singularity will be the second derivative of the delta function. So you get 1 minus c squared of x times gradient of x phi squared. You do the calculation, and this is, we want to eliminate this term. So we get what's called the conal equation. So the conal equation is simply the modulus of the gradient square is equal to 1 of c squared, and you have the initial condition for the phi. And this is, you're trying to solve a linear equation here. So it's a linear equation, but however, we're led to a nonlinear, but this first order equation. And that's actually easier to solve. Believe it or not, a nonlinear equation is easier to solve the linear equation itself. We need to solve a nonlinear equation to solve the linear equation. The Connell equation is very important in many fields. So let me tell you, and before I go on, the second singularity, which is called the transport equation for the highest order term here, it's called the transport equation because it tells you how much of the singularity is being carried. And also appears in kinetic theory, is this one. This is now a first order linear PD. So this is the equation. A0 is 1 if x dot omega is sufficiently large negative. To eliminate this singularity, you get that these coefficients must be 0. But this is a linear equation. It's much easier to solve, as we are going to see. So this is the transport equation and the Connell equation. I'm going to concentrate on the Connell equation and say a little bit about the transport equation later. Okay, and here you can apply the theory that you have learned. It's Hamilton-Jacobi theory. The Hamiltonian is, I will normalize it in this way. It's the principal symbol of the equation. And I'm going to take tau equal to 1. This is when h equal to 0. This is the sphere in the metric 1. There is a metric for the people who are familiar with metrics, and we'll talk about this soon, is that this is the underlying metric here that we're going to consider related to the sound speed. It's a multiple to the standard Euclidean metric. So you consider the Hamiltonian, I normalize so that when h is equal to 0, modulo c is 1 over c squared. This is what you want to solve this Connell equation. Because we want c, if c is the gradient of some function, then you solve the Connell equation. The Hamiltonian is 0. And so, but you have to find this phi. That's, okay, so here this Hamilton-Jacobi theory very quickly. You have seen this. These are the bicharacteristics. Also, in this case, there are the null bicharacteristics. I'm considering that this is equal to 0. And you take the integral curves of the Hamiltonian vector field. I've seen this before, with initial conditions so that you are on hc is equal to 0. You want to remain in hc is equal to 0. And the geodesics of this metric are the projections of these bicharacteristic curves on X space. This is another way to define geodesics. Take the solutions of the Hamilton-Jacobi equation for this Hamiltonian. You can also do this for a general metric. And the projections give you the geodesics of this metric. So the geodesics are usually defined to minimize locally length. So what is the length for this metric is just ds over c. And you can see you have a region of low velocity. When the velocity is low, the geodesics are going to try to go around because you try to minimize the time. The lower the velocity, the bigger the length by this. So you want to avoid regions of low velocity. And so the geodesics curve this way. It's particularly this happens when you have positive curvature. And you form lenses, and this creates problem, caustics, and so on. Okay, so how to solve the Connell equation? And this is a very easy thing in Hamilton-Jacobi theory. You start with x dot omega is equal to minus r, away from the support. And then you flow out. This is contained in the hc is equal to 0. And you take the bicharacteristic curves. There are straight lines outside the support of c. Support meaning c is equal to 1 outside. And here, Then you have these bicharacteristic curves. In X space, they are geodesics. Okay? And then you flow out by that. You flow out by the characteristic. And the flow out is a Lagrangian submanifold that you have heard before. This is codimension 1. And this is the flow out by the characteristics starting at these points will give you a Lagrangian manifold. And a Lagrangian manifold, you heard about this earlier. I will very briefly review it. A Lagrangian manifold is locally, every Lagrangian manifold is given by locally by x gradient of x phi. So you are in H, these characteristics are tangent to HC is equal to 0. So you start in HC is equal to 0 and you stay there because this vector field is tangent to HC is equal to 0. You stay in HC equal to 0. Remember, you just want C equal to the gradient of x of phi. This is a very brief sketch. I'm not giving all the details. So the flow out is given locally by in this way. In the projection, you have to have the projection to be diffeomorphism in X space locally. And that's the solution of the Conal equation. Very briefly, I remind you, this was already covered. Lagrangian manifold is an n-dimensional submanifold of Rn cross Rn in this case, where the symplectic form vanishes on tangent vectors. So this is a symplectic form. In this case, this is the Hamiltonian. So this is very important. This bicharacteristics stay in Hc is equal to 0. Therefore, this Lagrangian manifold is contained Hc equal to 0, is given locally by some phi. So you solve the Conal equation locally. So that's very simple. Using Hamilton-Jacobi theory is very simple, and symplectic geometry very simple to solve the Conal equation, the first order nonlinear equation. So let me point out also that there are problems to solve this globally because of the behavior of the geodesics. This is some nice examples drawn by François Monard, who is here, I believe. And this is not working. So in the example on this is the metrics here are these Gaussians. Here, for some values of k, so the geodesics are starting at a point in the boundary of the disk. In the k, for the k on the left, they behave very well. It's going to be called a simple metric. For other values of k, you develop the rays come together, the bicharacteristics come together. And in that case, you have what's called a conjugate point at the boundary, a caustic at the boundary. The rays come together, so you cannot solve the Conal equation globally. And in the third picture on the right, for the value of k 1.223, then you have conjugate points or caustics in the interior of the disk. So the behavior of the rays or the bicharacteristics of geodesics can be quite complicated, and you cannot solve the Conal equation in general globally, unless you have some special conditions. And like in this case on the right, on the left, sorry, you can solve the Conal equation globally. In that case, the geodesics behave very nicely. Okay, so the singularities of as I said, the philosophy is to follow the singularities. You have the singularity on this plane wave. Now the singularities are in t is equal to phi of x are on this hypersurface, t equal to phi of x omega. The gradient of phi is perpendicular to these distorted plane waves. So what does the phi measure if you measure it outside? Remember, the inverse problem is to recover the c. When after we interact with the medium, you observe what happens away from the medium. What can we recover? So we look at x dot omega is equal to minus r, say. I'm doing with time. And then This goes in the fastest direction along the geodesic. So you have the wavefronts, which are distorted wavefronts, not anymore planes here. And then if you can solve the conal equation globally, so if we assume that you can recover that globally, you can recover the distance function with respect to this metric between this point and this point, or between this plane and this plane. Because this is perpendicular, you're measuring the wave here, so you know the phi here, solution of the conal equation, you can measure this distance here in the metric, in this metric. I'm going to talk about this in more detail. So from knowing the singularities of the solution outside, after they interact with the medium, you can recover the geodesic distance between these two planes, or in these 2 points in particular. Okay, so this is the inverse problem, which is related to what's called boundary rigidity. I'm going to pose it in more generality in a minute. Suppose we know the phi of x outside this ball on the ball for x equal to r. We know the geodesic distance between 2 different points. We do this for every omega. Can we recover the sound speed inside? That's the inverse problem. And this is a problem that has been analyzed by geometers for metrics in general, and I'm taking just sound speed for simplicity, but the problem is also the same ideas can be applied to metrics. So this is the problem, the boundary rigidity problem. I motivated that problem. So you have a bounded domain in Euclidean space. You have a smooth function, positive function. You have 2 points in the boundary. The boundary distance function, and here I define it precisely, is the infimum of the lengths of all the curves joining the points x and y. So what is the length of a curve is given here, is by the superposition of the lengths of the tangent vectors, so it's given here precisely. And the inverse problem is, can you recover the sound speed inside knowing the distance function between 2 points in the boundary? This is the problem that we had from before. Here we have a ball, but that doesn't really matter. We're doing it in the ball. We know the geodesic distance. I define it precisely, because you're going along geodesics here, trying to minimize lengths perpendicular to the wavefronts. Can you recover the sound speed inside? So this is the inverse problem I want to talk in the rest of this lecture. It's boundary rigidity. And in general, it's not true because of problems with caustics. This is the problem when rays or geodesics come together. They form conjugate points. For instance, you have a point where the metric is the sound speed is very slow, very small. So that means the speed is very small, means the metric is very large. In order to find the distance function, will not recognize the points near x0 because it will take too much length to go through this point. The sound speed is too large. You're looking at this, 1 over c here. You're going to avoid that region altogether to compute the distance function, because the distance function measures the first arrival time of waves, the infimum of the lengths of geodesics. So you have this condition. This is taken because it's a compact set. This is bigger than, the distance is bigger than this. Then you cannot recover anything about the point x0 or near x0. So you need an a priori condition to recover the sound speed from the distance function. And the condition that has been proposed is simplicity. This is, I gave an example of simple metrics before. Simple means 2 points on the bound. You had 2 points in the boundary. There exists a unique minimizing geodesic joining the points. So you cannot have these conjugate points, and the boundary is strictly convex. So that means the conal equation has global solutions, not just local solutions. If the conal equation has global solutions, then and the boundary is strictly convex, this is an example of a strictly convex boundary. It's flat here, but of course it's strictly convex with respect to the metric, meaning the second fundamental form is strictly positive. You have 2 points in the boundary, the geodesic is going to stay inside. That's convexity. And the theorem was proven by Muhammad. This is a very nice result. It was one of the first ones. You can recover the sound speed uniquely and stably. It means that if you make an error in the distance function, you can compute the error in the sound speed if this is simple. So the problem is solved for simple metrics. However, this situation happens all the time in the pictures in the middle or the right, when you have conjugate points of the metric or what's called caustics. The geodesics come together and can form focal points. There are many situations like this. You cannot apply this result. The problem is that the boundary distance function does not measure all the information we can get, only the first arrival time of waves. Before I go to that, let me just point out very quickly, since you have heard about Lagrangian distributions, that this solution of the wave equation for the sound speed is an example of Lagrangian distribution. It's not conormal necessarily. The representation locally is given by this, when this is solution of the conal equation, and this is the solutions of the transport equation. I'm not going to talk much about the transport equation because it's quite easy to solve. But you can only solve the solutions locally, so you need Lagrangian distributions to patch this together. For every point, you can find a phase function, so the phase function may be different when you have caustics. In different directions, you have different phase functions, so you have to deal with that. So it's a Lagrangian distribution, not necessarily a conormal distribution. Okay. So the theorem that Muhammad proved from the point of view of the acoustic equation, if we know the solution for t sufficiently large, we can recover the sound speed if you have simplicity. So we can determine the proof is very simple, given what we know. You know the conal equation outside, therefore you know the distance function, and then you can recover the sound speed. But this is a very strong condition. Okay, and since I'm running out of time, I'm not going to talk about well, but maybe I should talk about this very quickly. The transport equation is given by a solution of this equation, and I said that before. This is a linear equation, so you integrate, it's a vector field plus lower order. You can get rid of the lower order by integrating factor, as we usually do for ODEs. This is an ODE along the geodesics, along the characteristics. So you solve explicitly this, and then you get the integration of A0 like we had before, but along geodesics, along the integral curves of these curves, I mean along these curves that are defined by this. So this leads to the geodesic transform. So the geodesic transform means you integrate a function along the geodesics up to the time where the geodesics exit the domain with boundary. So this is given a point and the direction, you integrate the function along the geodesic through that point in that direction until you exit. I'm assuming for simplicity, non-trapping. You can have trapping too, it has been considered, but for this talk, I'm not going to consider that. Okay, and then let me show, let me point out that if it's known that if this is injective in C infinity, this was also proven by Muhammedov. From the point of view of macrolocal analysis, if you consider the geodesic X transform, and this is a theorem of Guillemin that, although Alan attributed it to Guillemin and Stenberg, but I know it was Guillemin alone. If you take the projection, this is the Volcker conditions, but the Volcker condition in this case is satisfied if this is true. If the projection of the cotangent bundle from to take V to the geodesic from the point X in the direction B is a diffeomorphism, then this is an elliptic pseudo-differential operator with principal symbol very similar to what we had before, except for the C here. And I give this, I have a sketch of the proof here, and since I'm running out of time, I'm not going to give it. It's actually, you can give an explicit calculation to show that I star I is a singular integral, again, where this is the distance function from the points to the n-1. Before was x minus y to the n-1, and there is a Jacobian term here. It's very similar to that. And it's very explicit calculation. You can use the calculus of full integral operators to do that. But let me finish, since I only have 3 minutes, or 2 minutes, by mentioning a very interesting problem that has not been solved completely, which I hope the young people here take it, a very geometric problem. The problem with the distance function is that only measures the first arrival times of waves. You're taking the infimum of the lengths of all the curves joining the points. But however, suppose we look at all the directions. Take a point in the direction, shoot the geodesic, look at where it exits and the direction that exits. Take another direction, you do the same. Assume non-trapping. Okay, so suppose we know the point, the direction and point of entrance of the geodesic and the direction and point of exit. Can we recover the sound speed here, or the metric here? This is also a problem that is posed for metrics. And this is the travel time tomography problem. Suppose we know that information, and also we know the travel time, the length of this geodesic, plus this information, the point of entrance, direction of entrance, the point of exit, direction of exit. Can we recover the sound speed from this information? And that has been, for simple metrics, is the same as we had before. This is the same information as the distance function. It's easy to check. But for non-simple metrics, it's not. So what we have done is solve this problem by peeling an onion. We solve first the problem locally near the boundary, and then we march in. The reason is the following. Locally near the boundary, when you are a point here is convex, you don't see conjugate points. Because given 2 points, there is a unique geodesic joining them. You don't have the problem of caustics coming together. So you solve the problem near there, and then you march in. That's the idea. Very simple. And the theorem is that that works. This is a joint work with Plamen Stefanov and Andras Vashi. If it's strictly convex and the sound speeds are the same near this point, then the sound speeds are the same. We also get stability and a reconstruction method. And then the general theorem follows from this by this peeling argument. If the manifold is foliated by strictly convex surfaces, then you solve the problem here locally near the boundary. Then this is strictly convex. You march in, and you can keep marching in because you always have a strictly convex point. So the point is to march in once you know and we have a strictly convex point. You can keep going. You can keep going until we cover the whole manifold. And we assume that the manifold is foliated. An example of such manifolds where you have conjugate points is this example, for instance, for non-negative sectional curvature. You can have positive curvature. So the geodesics are coming together like the sphere, and this result will be valid. If the sound speed increases with depth, which happens in geophysics, it's also true. So there is a lot of cases that can be done. And let me tell you that the problem is really reduced to consider the integration along geodesics, joining points near the boundary, near where I'm going to finish with this, sorry. You just consider geodesics joining points here, near here. Not all the geodesics, that's the local problem. That's the main ingredient is this. There are a lot of technical work to be done. And then what we do is we're going to create an artificial boundary here. The reason is that the inversion formula, I star I is a pseudo-differential operator, but that's non-local. So even if the function is supported here, you need to know, to recover the function, you need to know away from that. So we create an artificial boundary to fix the domain. And this will be very close to the point where you're taken. We do a cutoff. We take only geodesics that are joining points in this neighborhood, close to tangent. And we show that this operator, which you have to take the cutoff here, is in the scattering calculus. It's an elliptic operator on the scattering calculus that Xuen defined in her lectures. The infinity here, as you go to the boundary, this is an elliptic problem here. I star I is a pseudo-differential operator, but degenerates as you get to the artificial boundary because these cones degenerate. They become tangent as you approach this artificial boundary. So you cannot apply the usual calculus, but however, you can show by taking 1 over x. X is the distance to the artificial boundary. You go from x to 1 over x, so you go to infinity. You show that you can apply, so you go from x to 1 over x here in this expression. You can show that this is in the scattering, it's an elliptic operator in the scattering calculus, so therefore you have inverted modulo smoothing. But if you are close to the boundary, it's a small domain, this will have a small norm, so you can invert it. Exactly. This is the local result. And then we march in. So this is an application of the scattering calculus. You get a degenerate operator as you approach this artificial boundary. And away from the artificial boundary, everything works fine. It's at the artificial boundary. But the artificial boundary, you can put it anywhere you want, near the boundary, and then you can invert. This is the inverse. We have a very precise inverse of the operator. And in fact, we have even done with some numerical analysis, some numerics. I will put this, this will be on the web. You can take a look, but it works very well in practice. Okay, so let me finish here. Sorry to go over time. 5 minutes. Yes?
Can you say something more about this marching in? So
Yes.
You know the metric in the first layer of the onion?
Yeah, so you know the sound speed or the metric in the first layer of the onion, and then since you know now you're looking at the global problem, so you know the integration of a function along all the geodesics. So you recover now the integrals of the geodesics in the second layer and apply the result. The only thing that you need to keep marching in is a strictly convex point. Once you have, but how do you find a strictly convex point? So we assume that you have it. For every point, there is a strictly convex. And this is satisfied for a lot of cases, as I mentioned before. For instance, for non-negative sectional curvature is surprising because then you have a lot of caustics, which is not admit for simple metrics. But the work, the real work, is done in solving this partial data problem. Once you solve the partial data problem, well, it's not trivial, but it's easy to march in. Sorry, I didn't have much time to go over the last part, but you can read the notes. I'm sorry to go over. Okay. Did I go too fast?
Can we see from making measurements if the simplicity condition?
Yes. For the distance function, for the distance function, you can know whether from the boundary, you can see whether it's simple or not. For instance, the Kroc show this that you can do it. One necessary condition is that the distance function must be smooth away from the x equal to y. It's not necessary, but it's very close to being necessary and sufficient condition. But you can see from the boundary. That's a very good question. The foliation condition, we don't know whether you can see it from the boundary a priori.